Hello all. Thank you for joining today's evening session. I think there are still a few members joining, but because we've got so much to get in today, I think we'll just get started, if that's okay. So again, thank you very much. So today we will be talking about, well, it will be the presentations from the EEFIT research grant winners. So EEFIT, of course, is the Earthquake Engineering Field Investigation team, the team of practicing industry and academic engineers and built environment professionals that visit disasters or research disasters after they've occurred in order to disseminate key lessons back to the professions at large. The research grant is an annual thing whereby EEFIT will award up to 3 grants to projects that are related to the field of post-disaster reconnaissance and learning from disasters. So we're really keen to hear from today's winners. Congratulations again to everybody. And again, if you're interested in either joining EEFIT or finding out more, then please do Google EEFIT, Earthquake Engineering Field Investigation Team. I should have started by introducing myself. I'm Josh McAboig. I'm the chair of EEFIT since this year. And just a few bits of housekeeping, if I could. If you'd like to ask a question, please go ahead and put that in the chat here. I think you're all familiar with Zoom, hopefully, but just there should be a chat button near the bottom of your screen. Go ahead and put chats there. I'll be monitoring those, and we'll be addressing questions at the end. With the exception of one of our speakers, Enrico Tebaldi, will actually have to leave after his presentation. So I'll do the bios in a minute, but Enrico will be going first, and we'll be taking Enrico's questions straight after his presentation. So if you have questions, don't hesitate. Please put them in the chat, and I will sort that out. Okay, so I will jump into the bios of our speakers, and I'm just going to read these ones out. So our first speaker will be Dr. Enrico Tebaldi. He's a senior lecturer of structural engineering in the Department of Civil and Environmental Engineering, and member of the Centre for Intelligent Infrastructure at the University of Strathclyde. Before joining the university in October 2017, he was Marie Curie Research Fellow at Imperial College London and postdoctoral researcher at Polytechnic University of March, University of Camerino, Louisiana State University, and at the Institute of Risk and Uncertainty of University of Liverpool. So it's a long set of accolades. It's a tongue twister. He is author or co-author of more than 50 journal papers in the field of earthquake engineering, structural dynamics, infrastructure risk assessment and monitoring, and has supervised more than 10 PhD students and postdoctoral researchers. Dr. Tebaldi's research aims at reaching a better understanding of the behavior of building and bridge structures under extreme loadings by also taking into account the stochastic nature of the loading environment and of the structural properties and exploiting the information from sensors. This effort can lead to safer, more economic and more rational design procedures and contribute to make the built environment more resilient against the impact of natural disasters. In the programme, it says for me to introduce all 3 speakers now, but I wonder if the bios are quite extensive. So maybe if we jump straight into Dr. Tebaldi's presentation, if you're ready, because I know you do need to head off afterwards, and then I'll continue the bios afterwards if that's okay. So over to you, Enrico.
Great, thank you very much, Josh, for the introduction, and thanks to EEFIT for this great opportunity to present here the research that has been conducted together with my PhD students, Pratik Kumar and Alessandra Orfeo. And I must also acknowledge the contribution of Amit Ahmadi from Tark Rubber Research Center. And also I would like to acknowledge the support given by the University of Strathclyde and my department, because this was, after all, an experimental research. It was severely impacted by COVID, but the department has given high priority to the project and let Pratik carry out the experiment even during the burst of the COVID crisis. And this helped to achieve some good results within the assigned time frame. I also would like to thank James Francis, our lab technician, who helped to set up the experiments I'm going to show you. So without further ado, I'm going to start the presentation and jump into the outline. Can you see it? I assume that if you don't stop me, you see my screen. So yeah, the presentation will first cover a brief overview of the problem of seismic damage to infill walls and techniques for infill wall protection. And then I will discuss the core, illustrate the core of the research on modeling of RC frames with infills and rubber joints, and the experimental testing of masonry triplets, and finally some conclusion on future studies. So I guess that most of you are familiar with the concept of masonry infill walls, and most of you also may know that these are usually considered as non-structural components in the buildings, alongside with cladding systems, piping, and other equipment. And these components contribute overall to almost 80% to 90% of the overall building costs. So they're very important, basically, as important as structural components. And because infill walls are often disregarded in the design stage, and they're not engineered properly, they end up being severely damaged during even relatively minor earthquakes. And for example, yeah, these pictures are taken from Aquila earthquake, but I guess that many reconnaissance reports from EEFIT show similar damages occurring in under other earthquakes in other locations. And these figures may be of interest to you. These are the tables taken from the recent and others recent publication, show basically that the overall cost for repairing infill walls in those buildings in Aquila that were not completely collapsed and demolished, but were repaired after the earthquake. So the contribution of the repair of the infills is of the order of 40 to 60% of the overall cost of repair of these buildings. So this gives you an idea of how important are the direct losses due to infill wall damage, and there is no need to mention how important also are the potential indirect losses arising from the damage to infill walls. I had the opportunity also to visit some towns in central Italy after the earthquake, notable earthquake sequence a few years ago, and I was in Fabriano and spotted lots of buildings that were severely, not really damaged in the structural components, but had this type of double leaf infill walls that collapsed. And not far from the building on the left, there is a school, which is a reinforced concrete buildings that was retrofitted prior to the earthquakes with the addition of high damping natural rubber dampers. These dampers were designed by Tark Rubber Research Center, in particular by Amit Damadi. And thanks to this, the school building didn't experience any damage during these earthquakes. So now, looking at these two pictures, one may already come up with the idea of why not combining these two systems, the infill wall and the dampers, the rubber-based dampers, into a single system that can exhibit a better performance under the earthquake, so that the infill wall is not damaged, and actually we are able also to improve the performance of the reinforced concrete frame by adding some source of energy dissipation. And this is the idea at the base of the use of rubber joints within the infill walls, as I will show you later. But first, let's make just a brief description of the techniques for infill wall protections that are already available or have been developed in the last years. And I've classified them in these two categories. The first one are the techniques aimed at increasing the infill resistance. Second one is the class of techniques aimed at minimizing the infill frame interaction. So in the first category, we have fiber reinforced polymers or use of any sort of reinforced plasters that are aimed to increase the resistance of the infill. But these techniques have several limitations, in my opinion, because they result in increased stiffness and forces in the system, which is very bad also for non-structural components, particularly for the acceleration-sensitive ones. And they often require strengthening on the frame members adjacent to the infills and are usually costly to implement. On the other side of the spectrum, we have techniques that aim to minimize the interaction between the infill and the frame, or increasing the flexibility of the infill. For example, using locked brick infills, introducing gaps between the infill and the frame, or using sliding flexible layers between the mortar joints or between the infill and the frame. These, in my opinion, are very advantageous, thanks to the minimal interaction with the building structural components, the reduced increase of global stiffness of the system, and the fact that in some situations they may add energy dissipation to the system. In Seismic projects was you funded the project that ran between 2013 and 2016, and within these projects, some of these techniques for protecting infills were explored. And among these techniques, the most promising one that emerged was the one involving the use of these rubber joints in the form of horizontal layers that basically divide the infill panel into a series of subpanels, and the vertical layers that are placed between the infill panel and the columns. TARC Rubber Research Center have developed two types of joints, DRS V1 and V2, that have this special shape in order to achieve a sort of orthotropic behavior, which is preferable to improve the out-of-plane capacity of the infill wall. And DRS V2 presents a series of pins in order to improve the bond between the rubber and the mortar. And then there are other types of joints that are commercially available and also made from recycled rubber in order to reduce further the cost of the technique. And in Seismic project, in particular, University of Padua have provided a proof of concept of this technology by performing a series of quasi-static tests in plane and out of plane. So basically, they built a series of reinforced concrete frames and filled them with different typologies of infills. So on the right, you see a traditional type of infill wall construction. On the left, the infill wall with the rubber joints. These have been tested first under in-plane loading by pushing them up to drift levels of 2.4%. That corresponds to a quite significant deflection for the system. And this has resulted in severe cracking in the traditional infill frame and also crashing in the blocks for the traditional infill frame. Whereas you see for the same level of deflections, the infill wall with the rubber joints experience almost no damage. On the right, you see the static responses of the two systems, and it's already very evident that the system with the rubber joints is characterized by more stable and fixed cycles with an equivalent damping ratio, which is of the order of 10 and 12%, and is significantly higher than the one that is achieved normally in traditional infill structures. And then obviously minimizing the in-plane damage has also benefit in terms of improving the performance under out-of-plane loading. And further tests carried out at University of Padua has shown how with the rubber joints it's possible to achieve out-of-plane capacity that are comparable to the ones that will be obtained for the traditional infill case. Now, in Seismic project has provided a very nice proof of concept and demonstration of the capabilities of this technology, but has also left us with a series of knowledge gaps that need to be filled. And here comes the work carried out thanks to the EEFIT prize on advancing the modeling of RC frames with infill rubber joints and on experimental testing for characterization of rubber mortar joints. So I'm going to describe this now, starting from the first. Whose research objectives were to develop advanced modeling strategies for the assessment of the type of structure at hand, and also develop simplified modeling strategies suitable for investigating larger structures. And then another objective was to provide some recommendation for the optimal design of the rubber joints. So now there are different techniques that can be adopted for modeling the infill panel with the rubber joints. And we have explored, in particular, a mesoscale modeling approach, a macroscale modeling approach, and a microscale modeling approach that I'm going to discuss more in detail in the next slides. So the mesoscale modeling approach for the infill construction basically involves using a set of solid elements, this one, for describing the bricks. So basically for each brick, we have at least one solid element, but usually we have more than one. And these solid elements are then connected one to each other through zero thickness interfaces. So that corresponds basically to shrinking the actual stiffness of the joint, that is a few centimeters, into a zero thickness element without losing much of accuracy in the response assessment. And then we use also interfaces for describing the interaction between the fill panel and the adjacent RC members. And for the RC members, we can use different type of description. In this work and this research that has been recently published in Engineering Structure, in particular, we use, again, solid elements and embedded rebars for the steel reinforcement. So now the core of this modeling strategy is the description of the zero thickness interfaces that must be capable of describing the main failure modes typical of masonry, such as cracking under tensile stresses or shear failure once the cohesion and the friction capacity of the bond is overcome. For this purpose, we have employed interfaces available in Abacus with an uncoupled elastic response and with some damage model that describes the peak and post-peak behavior. And the modeling properties can be calibrated to some experimental tests carried out on the components. And here you see the simulation, we can call it calibration, but also validation of the modeling strategy by means of comparison between numerical results and experimental results from in Seismic project. I've shown you some of these earlier. For the case of the bare frame, the traditional infill, and infill with the rubber joints. And there is a very excellent agreement between the numerical and the experimental test results. Here are shown some results for the simulation of the case with infill and rubber joints. And in particular, here you see the deflection shape of the model exhibiting significant deflections in correspondence of the zero thickness interfaces that are located where the horizontal rubber joints actually are. And note also that there is a very good agreement between the crack, the few minor cracks forming in the blocks and the cracks observed experimentally. And on the right, you see the so-called pushover curve, so the load displacement curve under in plane loading, for the case of bare frame, traditional infill frame, and frame with infill and rubber joints. And this shows that the rubber joints are effective in basically reducing the interaction, in increasing the flexibility of the system and reducing the interaction between the infill and the frame, so that the response of the system is quite close to that of the bare frame, as sought. So we have also done some work oriented towards the definition of the optimal location and the properties of the joints. For example, here we have considered the case of horizontal rubber joints only, horizontal and vertical rubber joints, or vertical rubber joints with very high stiffness or low stiffness. And here is the comparison of the pushover curves that are quite similar, with the lowest curve corresponding to the case of vertical joints with low stiffness. But the differences are more appreciated if we look at what happens locally in correspondence of bricks and also in correspondence of the frame. And we can say that using vertical joints with low stiffness as well as horizontal joints provides an improved, the best solution in terms of minimization of the compressive stresses in the blocks and reduce the cracks between the blocks. So from this figure, you can appreciate how this modeling strategy, that is quite complicated and computationally expensive, provides very useful insight into the the behavior, local behavior of the component of the system. However, you can already have an idea of how computation expensive can such a technique be, so that it cannot be really employed for simulating the response of larger scale structure under dynamic loading. And for this purpose, we've been doing some work towards the development of a macro modeling strategy for simulating the problem at hand, using a reduced number of degrees of freedom and a few parameters required to define them. Some of you may be already familiar with the use of strat elements for simulating the response of frames with infills. More sophisticated elements, such as these macro elements here, have been developed throughout the years. And we have worked together with Callio and Panton, together with Pratik, and we have, in particular, used their macro model for our problem. Their macro model consists in a simple articulated quadrilateral, shown here, with a diagonal link and a series of links located along the edges that can be used to represent, to describe the interaction between adjacent macro elements when subjected to sliding action or axial actions. And this type of macro element that has been recently implemented in OpenSys is capable to describe the most critical failure mechanisms, characteristics of masonry, of infield structures, and particularly the masonry component, such as the masonry crashing or the sliding crack formation, the diagonal cracks formation, as well as the detachment between the infill and the frame. Obviously, we needed to expand a bit this macro element in order to make it suitable for our problem, and there is no time really to describe in detail this research that is going to be published soon. Anyway, the most important critical parameter for these elements are the parameters that control the behavior of these springs here that represent essentially the behavior of the horizontal joints, where most of the flexions are localized, basically. So here you see some results in terms of simulation of the Seismic test for the case of the traditional infill or the infill with the rubber joints using different types of meshes. And you see how with a few macro elements, even 4 macro elements is the minimum amount that we need, we can capture the basic mechanism that involves significant deflections in correspondence of the horizontal rubber joints, as well as separation or penetration between the panels and the vertical rubber joints. We have made some comparisons also, with the pushover curves and the cyclic responses, and the proposed modeling strategy provides a very good fit to the experimental test results. And if we use also force-based formulation for the adjacent column and beam members, and this allows us to have an idea of the internal forces arising within the reinforced concrete frame due to the interaction with the infill. And in general, we have observed that the case with rubber joints results in reduced internal forces in the columns compared to the case with the traditional infill, or also even to the bare frame. This is very interesting. It's the comparison between the force displacement curves obtained using the mesoscale three-dimensional advanced modeling strategy and the macro scale modeling strategy using the macro element that we have developed. And you see the two curves for the different systems investigated are very similar, but note that with the advanced modeling strategy, we require about 85 hours of computational time to reach the target displacement, compared to only 24 seconds that are required by the DMEM model that is characterized by only 30 nodes for the case of the Seismic test. So now I'm going to move quickly to the other topic, the experimental testing of masonry triplets. And the research objectives of this task were to investigate the energy dissipation capabilities of the mortar rubber joints, characterize experimentally the theoretic behavior and capacity of the triplets with mortar rubber joints, and calibrate alternative models for simulating the response of these devices and then fill the frame. So basically what we did first was to cut some pieces of rubber from the rubber joints kindly provided by Amit Ahmadi at ARC, and we tested the first the rubber under uniaxial tensile loadings in order to produce this tensile testing response and also to evaluate the relaxation behavior. Then we cut other pieces and produce these quadruple shear test pieces that have been tested under basically simple shear loading to produce the hysteretic curves on the right, and also we have evaluated the relaxation behavior. And then Pratik has produced a series of triplets made by using simple all the English bricks that were available locally, and bonding them using a traditional technique involving only a mortar, or using the mortar rubber joint alternate layers. And then we have developed a quite unconventional test setup for testing these triplets. This setup is unconventional in the sense that the traditional test setup, the one acknowledged also by the Eurocodes, allows to test the triplets only by under monotonic loading. Here, on the other hand, by adding a few threaded bars and plates, we are able also to test the triplets under cyclic loading, which is very important in order to gain insight into the theoretic behavior of the joints. And basically, through this hydraulic jack and the plates and the threaded bars, we are able to impose first some different precompression levels, and then with the vertical actuator, we can test the triplets, and particularly the joints under shear loading. So here are some test results for the triplets with mortar joints under monotonic loading upper part and under cyclic loading lower part. And here are the results, more interesting, that we obtained for the case of the mortar rubber joints. In terms, again, of monotonic loading, obviously the capacity increases by increasing the precompression level, and under cyclic loading. We have more results than the one shown here. In general, we have observed that for all the tested triplets, failure occurred in correspondence of the bond between the rubber and the mortar, despite the use of these pins that are supposed to increase a bit the bond capacity. So this bond is actually the weakest link of the system. This is a quite important result. And we have produced these curves that show how the shear stiffness of the system reduces quite significantly for increasing strains, but this is well known for typical rubber, is the so-called pain effect. On the right, you see how the equivalent damping of the system is actually quite high, so of the order of 20 to 30%, the damping ratio, and it actually increases with the strain. So this is also a very important result because it shows that if a property is exploited, the rubber can allow to achieve very significant amounts of energy dissipation in the system. We have also been able to fit the Moore-Coulomb failure envelope, the criterion Moore-Coulomb for the failure of the bond in the case of traditional mortar joints or mortar rubber joints, and these have been used to inform a numerical modeling strategy. This numerical modeling strategy is a micro-scale strategy because here we are using solid elements also for describing the behavior of the joints. This is different from the mesoscale approach where we use zero thickness interface. And this type of strategy is unavoidable for the problem at hand because the models available for the interfaces are overall quite poor and are not able to capture the very complex behavior characteristic of the rubber joints. Again, some comparison with experimental results here for the traditional mortar joints. And then we move to the rubber case. And obviously, in order to describe the rubber, first we need to fit a reliable model for describing the material. And this has been done considering the test carried out on the rubber pieces. And we've been able to fit quite well a material model that employs in parallel a Yeo hyperelastic material model plus an hysteresis model from Bergstrom and Boyce. And the parameters of these have been calibrated against tensile test, shear test, and relaxation test, with a very good fit being obtained. And then using this model of the rubber, you see here we have developed the model of the triplets, considering also the actual thickness of the rubber as well as of the mortar joints, mortar layers. And on the right, you see the comparison between finite element analysis and experimental results for all the cycles of deformation imposed, considering different amplitudes and also different precompression level. And we are very surprised that there is an almost perfect match between experimental results and finite element analysis results. This is even too good for us. So some final remarks on the experimental test. We have developed an experimental setup that is quite unconventional and that has allowed us to investigate the cyclic behavior of the triplets. We have found that the rubber layer mortar bond is the weakened component of the triplets. And this is very important. It means that we need to do some more work in order to enhance the bond behavior in order to be able to fully exploit the capabilities of the rubber in dissipating energy, even though we must say that failure of the bond doesn't imply failure of the system. And we can still rely on the frictional sliding to dissipate energy. We have also found that the rubber compound is very dissipative and characterized by very good damping capabilities that needs definitely to be exploited in order to protect the frame. And we have defined, calibrated a micro modeling strategy that has provided a very excellent fit to the experimental result. So now this leads me to the conclusion of future study session. We have shown through experimental numerical tests the potential of rubber joints for protecting fields and enhancing the performance of in-field frames through a series of mechanisms that involve minimization of in-field damage, reduction of interaction between in-field and the frame, and reduction of global stiffness of the system, and enhancement of energy dissipation capabilities of the system. We have developed numerical model strategies with different level of complexity in order to investigate not only the local behavior of the components through the use of micro mesoscale models, but also the performance of larger scale systems thanks to macro models that are characterized by very few degrees of freedom. And then the experimental test results have been very useful for calibrating FE models, and they will be used in future studies. And in fact, here comes a long list of future tasks that we will be working on, starting from the modeling of the combined in-plane and out-of-plane behavior of the system. And then we will develop strategies for the optimal design of the geometrical and mechanical properties of the joints, investigate further the dynamic behavior and damping capabilities of measuring field frames with rubber joints. So basically, we're going to evaluate what is the level of composite damping that can be achieved, which is somehow in between the damping of the rubber, which is of the order of 20%, and the damping on the frame, which is of the order of 5%. And we know that we're going to achieve levels up to 10 to 15% of damping ratio. And then we're going to evaluate the global seismic performance of a wall building with infill walls and rubber joints using the recently developed macro modeling strategy. And then use this to perform fragility analysis, life cycle cost-benefit analysis to further prove the effectiveness of rubber joints. And finally, in order to cut the cost, we are going to develop with ARC low-cost joints made from recycled rubber. So this basically concludes my presentation. I hope it was of interest to you and that there are questions. Thank you for your attention.
Thanks a lot, Enrico. Can you hear me, by the way?
Yes, I can hear you.
Great.
Stop the screening for now.
That's okay, you can leave that there if you want. I can't see any questions in the chat, though I do see Roberto has a hand up. So Roberto, go ahead.
Hello, Roberto Gentile from UCL here. Enrico, thanks for the presentation. It was very interesting. And I'm just curious about the new strategy to model in fields. So the question would be, how much more complicated is that with respect to single strat or multiple strat models? And especially, can you with the same macro modeling strategy, can you account for traditional infills and special infills as well, like sliding or the ones you have developed? Thank you so much.
Yeah, very good point. Of course, I haven't got the time to show the results of the calibration study validation for the macro element models of Carrion and Panton. But basically, we have with the same macro element that is now available in OpenSys, you can by properly tuning the parameters, which requires a bit of work anyway, you can really simulate both the case of traditional infills and the case of traditional infills with rubber joints. So we're using an element that is already available in OpenSys. There is only a bit of work to be done in terms of calibrating the parameters. It's unavoidable to have, you have definitely lots of parameters that you need to calibrate if you want to control well also the aesthetic behavior of the infill. So yeah, in some sense, it's true that the model is a bit more complicated than a classic traditional strat element that is typically used in the assessment of infill frames. However, yeah, the typical strat elements don't work well, cannot be employed as they are for the case of infills with rubber joints, because they would not be able to capture some local mechanisms such as the punching of the sub panel into the vertical rubber joint and then into the columns. So the increase of forces transmitted, horizontal forces transmitted from the panel to the frame, and also other local mechanisms. So I would say that, and also there is a work of Di Trapani on the use of truss elements for describing infill joints, infill panel with sliding joints. So if you look at the global response of a wall building, maybe you can still resort to some very simple description using the truss elements. But then if you want to look at vulnerability of components like columns and beams, you really need at least the macro element model that we've been working on, if not the mesoscale description that is unfortunately too computationally expensive to be employed for seismic analysis of a wall frame system. And I think I wanted to say is that another limitation that we are currently addressing of the macro element model is that so far it describes only the in-plane behavior, whereas obviously in a real building, the in-plane behavior interacts and is conditioned and affects the out-of-plane response as well.
Thanks so much.
Thanks for that. If there's no other questions, and in the interest of time, we should move on. But I do have one question I can't resist the temptation to ask, which is your thoughts on, this looks like a really useful technology, and your thoughts on the barriers to implementing this technology in practice. So what are the next steps to actually see this being used in buildings? I'm particularly thinking about what you mentioned on the out-of-plane failure, and how effective it is to preventing that out-of-plane failure. I think you said that it had comparable capacity to a traditional wall, in which case that's fine. But if it's less capacity than a traditional wall, could that actually increase your possibilities of that out-of-plane failure, and obviously the risk to life that might bring? And also the other question about, you have less cracking of the mortar because obviously you have your deformations are concentrated in the joints, but do you then still get permanent slip of those joints, the rubber joints? In which case, does the panel still need to be replaced if you do get that permanent slip? So, sorry, two questions, and I said we didn't have much time, so you can answer it quickly.
Lots of very interesting questions, and could take hours to reply to all this. But yeah, to cut short, barriers to implementation. Yeah, we're trying to address this. Also engaging with some companies such as Farad, for example. Unfortunately, we've been unsuccessful with an application for Innovate UK funding. But yeah, the idea is really to come up with some simplified modeling strategies and also some simplified formula for the design of the system. And eventually we will do this, and this hopefully will help practicing engineer uptake of the technology by practicing engineers. Yes, and And so it's good that Hamid Ahmadi, who contributed to the development of this technology, sits also in the N15129 panel, and that is related to the development, the characterization of dissipative devices. So its position there is really useful for the development and uptake of the technology, in my opinion. And the autoplane behavior, yes, is something that we're going to address more in detail very soon. But yeah, we don't envisage a problem because also these experimental tests that have already been carried out in Padua have shown that the autoplane capacity is comparable. And these tests were quasi-static tests. In reality, if you account also for the enhanced damping coming from the rubber, the demand on the panel, the autoplane demand is also reduced. So this should also improve further the performance compared to the traditional infill. The other interesting point was about the breakage of the bond and the sliding. So basically, in the model, the model, I can probably share again the screen. So what you see here, for example, it's only an apparent sliding between one subpanel and the other because we're using a zero thickness interface element for describing the rubber joint. So in reality, you have to think at a rubber deforming in a simple shear, like in this test here. So this is so you can think at one panel located here, sliding over the other panel located here, for example. And all the deformation is concentrated on the rubber. So if the bond is sufficiently strong, the bond between the rubber and the mortar, then all the deformation are located in the rubber, and they are simple shear deformations. If the bond fails, then what happens is that you have sliding between the rubber and the mortar interface, but it doesn't mean really that you necessarily have to replace the panel. And in fact, there are some technologies that use sliding joints instead of rubber joints for protecting the infields. But autoplane behavior may be a concern in these situations, and so it may be this may reduce a bit the increase the vulnerability under autoplane loading, having not having a restraint provided by the rubber in the autoplane direction. I hope this answers your question.
Absolutely, yeah, that was really fascinating. Thank you for doing that and doing it in under 5 minutes. So thank you. And thank you for your presentation, Enrico. That was fantastic. I know you need to move on, so please feel free. But thank you very much.
Thank you very much for your attention, again, for the opportunity to present. Thanks.
Thank you.
Bye, everybody.
Okay, so if we could move on to Dr. Gianluca Pescaroli, if that's okay, we'll do that one next. So Gianluca, if you're ready, there you are.
Yes,
I'll read
the presentation will be start from Gemma, from my colleague.
Is it okay? All right, no problem. It's a different order here, but that's not a problem at all. So we'll go for Gemma then, if that's okay. So I'll read both of your bios now as well. So for Gemma Kremen is a lecturer in risk and resilience engineering at UCL, who specializes in developing statistical tools to support decision-making related to seismic activity and other natural hazards. She's currently working to quantify, model, and communicate disaster risk within the GCRF-funded Tomorrow Cities Hub, and is also contributing to the ongoing development of next-generation earthquake early warning systems within the EU-funded Turnkey project. Prior to joining UCL, Gemma worked at the University of Bristol on improving understanding of the seismic hazard and risk associated with UK shale gas development, and she completed her PhD in earthquake engineering at Stanford University in 2019. And then I'll do Gianluca's bio here as well. Dr. Gianluca Pescaroli is assistant professor and lecturer in business continuity and organizational resilience at University College London. His research investigates how to build and improve the continuity of operations during disruptive events, how to minimize their impacts, and how to increase the resilience of the public and private sectors. Gianluca's work is impact-oriented aiming to bridge academia and practice. He has contributed to strategic documents such as the UN Office for Disaster Risk Reduction's Guidelines on National Risk Assessment, and he was one of the lead authors of the flagship report Science for Disaster Risk Management 2020, drafted by the European Commission's Joint Research Centre. In 2020, he became the director of University College London's multidisciplinary master's programme in risk, disaster and resilience. So, two fantastic speakers, and Gemma, if you wouldn't mind kicking off.
So thank you, Josh, for the introduction. So today I'm going to talk about integrating earthquake early warnings into organizational resilience. So I'll do the first part of the talk, and then Gianluca will finish off. So when we're talking about earthquake early warning, the first question we ask is, well, what is earthquake early warning? So we can succinctly describe earthquake early warning as a set of seismic sensors and mathematical models or algorithms that can process real-time information about earthquakes as they are ongoing. So the idea is that we have a rupture that occurs, and the first type of wave that will emanate from this rupture will be a P wave. And then we can have seismic sensors that are located close to the rupture area, which can detect the P wave. And then based on information provided by the P wave, we can use algorithms to translate that information into estimates of the earthquake's location, its magnitude, and then also its ground shaking potential in a particular area. And this type of approach to earthquake early warning is called a regional or a network-based earthquake early warning approach. But we can also have an on-site approach where we have one seismic station that's located close to a particular structure or infrastructure of interest. This detects and processes the incoming waves, and then algorithms are used to translate that information then directly into ground shaking estimates at the particular structure or infrastructure of interest. Then the next component of earthquake early warning is the decision module, where we take all of the information that we've generated and processed in the previous steps and use this information to make a decision on whether or not an alert should be issued so that people can take protective measures before the stronger S waves from the earthquake actually hit their location or the region of interest. So that's just a background on what earthquake early warning is. Now, what we did is we did a general literature review on different methodological approaches to earthquake early warning across the world. And what we identified as part of this literature review is that there's 9 earthquake early warning systems currently in operation around the world, but there's a further 13 that are being actively tested. And these figures are evolving day by day. Now, something that we noticed in particular throughout our literature review was that there's very little earthquake early warning currently operational in Europe. So we decided to do a feasibility study for earthquake early warning in Europe, understanding which areas of the continent could particularly benefit from this type of infrastructure, with the idea of informing future implementations of this type of technology across the continent. Now, what we found as part of our feasibility study was that earthquake early warning could be particularly appropriate for areas in Turkey, Italy, and Greece. Now, the feasibility study was done on the basis of 3 criteria. So the population that lived near a particular site and was exposed to earthquakes that might affect that site, the shaking that that particular site might experience from nearby earthquakes, and also the lead time, the amount of time somebody would have to react to an earthquake early warning alert before the strong shaking from the earthquake hit them. Now, as part of our literature review, we also looked at the underlying algorithms associated with each of the operational earthquake early warning systems worldwide. And I'll go into a bit of detail on various ones of these algorithms in the coming slides. So let's look at how these algorithms detect and locate earthquakes. So some of the algorithms use data from triggered stations. So this means they look at all the stations that have so far detected a P wave from the incoming earthquake, and then use that information in a grid search to determine where the earthquake might be located. Other algorithms also make use of the locations of stations that have not yet been triggered, so have not yet detected a P wave, and they use this information to better constrain the location of the incoming earthquake. We also have algorithms that make use of geodetic observations to determine earthquake depth in particular. We also have algorithms that use templates of ground shaking and try to match the observed ground shaking with the most closely fitting template to determine the earthquake location. And then we also have algorithms that rely on data from just single seismic stations. So various algorithms that we showed on the previous slide are associated with these different methodological approaches. Now, something we were particularly interested in our literature review was the treatment of uncertainty at each stage of the earthquake early warning process, because each of those estimates of location, magnitude, and ground shaking will be associated with a certain level of uncertainty, and that uncertainty is particularly important when we get to the decision-making part of earthquake early warning, understanding whether or not we should issue an alert. So what we found is that very few of the algorithms we studied actually capture and handle and propagate the uncertainty associated with the earthquake location estimates. So Virtual Seismologist and Presto are the algorithms we found that actually handle this uncertainty, and they both operate within a Bayesian framework. Now let's move on to how these algorithms estimate magnitude. So what we found is that some of these algorithms estimate magnitudes using empirical relationships between early information provided by the P wave and the magnitude. Then some of them use a longer time frame using similar empirical relationships between the P wave information and the magnitude, but just a longer time frame of the P wave information. And of course, these are more accurate, but if we're using a longer amount of P wave information, we're therefore reducing the amount of time that people have to react to an alert. So there's a balance there between accuracy and timeliness always in earthquake early warning. Some algorithms, again, use geodetic observations. There's also some algorithms that use empirical relationships between rupture length, which they estimate, and magnitude. And then other algorithms that use data from just a single seismic waveform. So again, a variety of the algorithms we studied were associated with these different methodological approaches. And again, only a few of these algorithms actually handle uncertainty. So it's again, Virtual Seismologist and Presto, both of which operate within this Bayesian framework. Now moving on to ground shaking estimation. So as you might imagine, a lot of these algorithms, particularly the regional ones, they make use of ground motion models or other types of attenuation equations, which relate the estimates of magnitude and location to potential ground shaking in a particular region. Other algorithms use ground motion recordings and then interpolate the ground motion recordings to determine potential ground motion amplitudes associated with the incoming earthquake. We also have algorithms that use data from initial seismic waveforms, either from many stations or from single stations. And again, only a few of the algorithms handle and propagate the uncertainty associated with the ground shaking estimates. And it's important to mention here as well that Virtual Seismologist is actually the only one we noticed that actually propagates the uncertainty from the magnitude and the location to the ground shaking estimate as well, which is also important. So let's move on to the final component of an earthquake early warning system, which is the decision module. So how do these different algorithms make decisions on whether or not an alert should be issued for an incoming earthquake? So what we saw is that some of the algorithms make a decision based on the predicted magnitude of the incoming earthquake. So a decision rule in this case might be trigger the alarm if the predicted magnitude of the incoming earthquake exceeds magnitude 6, for example. Then other algorithms also combine the magnitude information with epicentral distance to make a more nuanced decision on whether or not to issue an alert. And then other algorithms make use of ground shaking estimates and also seismic intensity measures, which are derived from the ground shaking estimates. And here's a variety of algorithms associated with the different methodological approaches. But let's just focus here on one thing in particular, which is the different metrics that are used to make a decision. So all of these metrics are seismological parameters. And this makes sense if we consider the history of earthquake early warning, because earthquake early warning was originally developed by seismologists. But none of these metrics explicitly account for damage and loss, which are very important when we consider an earthquake early warning system, because the consequences of the earthquake will, of course, be measured in terms of damage and loss. And if we think about a false alarm, so where an alert is falsely issued, this should be kind of defined in terms of an earthquake that does not cause any damage or disruption to people's lives. And if we're not explicitly measuring our decisions in terms of damage and loss, then we actually increase the risk of introducing these false alerts into our system. Another thing to note about these metrics, so magnitude, epicentral distance, ground shaking amplitude, none of these are particularly intuitive for the general public. And this can sometimes inhibit the general public's engagement with earthquake early warning systems in general. So based on our kind of identifications of the limitations associated with the decision module in earthquake early warning in particular, we proposed an advancement in conventional earthquake early warning systems, which was to use risk-based decision metrics for the decision module. But not only that, to use risk-based metrics that were of particular interest to stakeholders and metrics that stakeholders could understand so that they are better engaged with the whole earthquake early warning process. So on the basis of this recommendation, we actually went ahead and proposed our own risk-informed decision-making approach for earthquake early warning. So the first step involves taking seismological estimates from our earthquake early warning infrastructure, which are the conventional outputs of operational earthquake early warning systems around the world. But that's really where the similarity with conventional systems ends. Because what we do is we then take earthquake engineering assessments, combine the seismological parameters with these assessments to then determine estimates of the damage and loss associated with the incoming earthquakes. And then what we do is we take advantage of performance-based earthquake engineering to ensure the metrics are interpretable to stakeholders. So we use metrics here like repair cost, repair time, and casualties. Then the next step involves taking the consequences, which are summarized in the consequence matrix, and translating them into the decision matrix by also accounting for stakeholder input. So stakeholders can tell us, which of these metrics are they particularly interested in? Would they prefer to minimize casualties over minimizing downtime or vice versa? And then we can account for this in our ultimate decision. So then the output of our risk-informed decision-making approach is the optimal action. We either trigger the alarm or we don't trigger the alarm based on ultimately the incoming seismological information from the earthquake early warning system that has in the meantime been translated into engineering-based damage and loss predictions. So we did this assessment for a hypothetical school located in California for various values of the incoming ground shaking that could be associated with an incoming earthquake. and the results are shown here. And what's obvious from this graph is actually the optimum decision for a particular level of ground shaking associated with the incoming earthquake can change depending on stakeholder preferences towards the underlying metrics. So here we focused on casualties, downtime, and repair cost. And what we saw is that if the stakeholder prioritizes the minimization of casualties, they'll actually end up triggering the alert at a lot lower level of shaking than they would if they prioritized the minimization of downtime, for instance. So stakeholder input is really important in the earthquake early warning process. Now, the beauty of this type of methodology is that we can compute this plot ahead of time before any earthquake happens. And what we do in real time is simply just consult this plot with the estimate of the incoming ground shaking, and we can make efficient decision-making in real time. And then another advantage of this type of approach is that we can simply code this as a plugin, and it can be used in operational earthquake early warning systems worldwide. So as part of another literature review we identified challenges associated with earthquake early warning across 4 different dimensions. So in this talk, I covered the operational sphere, or the technical part of earthquake early warning in particular. And in the next part of the talk, Gianluca will talk about the other 3 spheres. Thanks very much for listening.
I'm going to present the outcome of our project integrating earthquake early warnings into organizational resilience, and I will go to the case studies. So in reality, my presentation will focus on some other aspects, so more the practical implication of the study. But the point is that I'm going to do that under social science perspective. As you have heard, my background is very different from the one you heard until now and that you are used. I've befriended the research group on cascading disasters back in 2016, worked on national disaster risk assessment guidelines for the United Nations, in particular worst case scenario assessment, contributed to Science for the Around 2020, and I've been working to other things with the United Nations, such as definition and classification review. I'm always happy to have a coffee with colleagues in engineering and try to work more on the interdisciplinary side. And my presentation will focus a bit on that to show you how we can merge the technical components of earthquake early warnings towards something more practical on the management of the interruptions. So first of all, I will try to give you an overview of what we mean for resilience in terms of continuity management. So not the blue sky thinking, but something how we practically integrated that in planning. The second steps we are going to do is that I'm going to explain you how we translate that practically in a methodology for assessment. And then I will show you some preliminary results of one of our last study. So the political and governance sphere, social behavioral sphere that we are assisting are technically something that is referred to the fact that technology is important, but it's context driven and socially determined. It means to say that you can have the signal, but the signal has to be translated in procedures and have to be translated by people and have to be codified and have to produce behaviors. Otherwise, the signal itself is not going to work. A signal itself needs to be aware of what are the context dynamic. It means, look at this picture there. So if you think about what we're doing with the shoes can be different in each single reality, right? Think about that. And most of all, which are the common vulnerabilities in the 2 pictures you're seeing? So it's not just a matter of the hazard itself. So in one point, the water or the shaking, or the other side, what we don't see, but it's the problem of how the signal is released toward the societal vulnerability. So for different, for example, levels of wealth, for different level of communication, for different level of education, for different levels of organizations and practice and governance. So when we are thinking about the operational component, then we see this other spheres in terms of society and how society codified the signal and which are the conditions for which the signal is codified, translating in action. So I work in particular on continuity management and disaster management. Means think about how reality changed in the last 20 years. So we were used to think about disaster management, just there is the shake. We take action to the shake because people are hurt. However, the way we approach it in the field of continuity management, so how we keep things going, what we're going to do and how we are going to use the signal, it means that we start to think what is happening at the same time. So how can this action be referred to stress on the response systems, and also how to mitigate disruption to the basis of what we are doing now, so to the technological basis of every single action we are taking. That means, for example, we are talking now toward internet and Zoom. We already had technical issues for which we shifted from one platform to the other. But at the end of the day, we need energy, we need communication, and we need logistics to keep operational. So in all this context is what we are doing to keep the context going, how we are gonna allow the response to the shapes. So how the signal is gonna process towards society, toward organization, to be translated into action. And how can we use that to minimize the disruption, not just in terms of life losses and damages, but also how we keep things recovering faster, and how we can use technology or also prevent and mitigate disruption on the technological side, so on the infrastructure side. So we need to think, most of all, what is business continuity? What is business continuity? This is like something that I approached in the last year. And first of all, is the capacity to continue to deliver a product and services within a setable time frame during a disruption. So, and disruption is an incident caused an unplanned negative deviation. Sorry for this. I'm gonna change the setting, but the deviation and the timing, where the disruption of the incident is what are we gonna act upon to do to support organization to keep running. So how the signal will be transferred to minimize the disruption. You can see there in the fun dog. It's simply, we're going to point A to B in our everyday life. So the problem from a business continuity perspective is how we are going to use the signal to allow an organization to minimize the disruption and integrate it in planning. So the tools business continuity works is knowing better the organization toward a planning process that try to understand which are the critical functions in each organization and what are the things that need to be recovered faster. Otherwise, we have increased loss and increasing impact. So it's like when you are in a fight, if you know which are your critical points of failure, you can act then to protect them and to get the hit better. So I'm used to think as business continuity in a process that aim to contain physical damages, financial losses like downtime cost. So how much is going to cost for a certain organization to be down? The loss of productivity, the need for communication and reputational aspects. And continuity management is applied also to the public sector, like with critical infrastructure, like emergency facility, like fire stations, hospitals. And it implies the knowledge of the internal process of each organization to go beyond it. So is often considered, for some of us, the dark side of the force of emergency planning and management. So think you have an emergency, you have the first response, how to keep the incident under control, limit the life losses, limit disruption. And then on the organizational side, you need to activate continuity management to keep the organization going, minimize disruption, and keep the service going. In the UK, for example, continuity management is mandatory for all critical infrastructure and first response facility with the Civil Contingency Act. So you need to take this action. Let me see now if the slide goes back to normal. Yeah. So we can see the benefit are like compliance in a context where there is compliance request, like here, the example I just made, downtime reduction. So it means that you are less likely to bankrupt because your losses will be reduced, reduce exposure of employees, the protection of your market. Think you are in the private sector. If you get disrupted for 2 days instead of 2 hours, maybe you're losing the reputation. Maybe you're losing clients. And overall, it helps to, knowing better your organization to maximize and producing a better output of what is developing. Okay. So business continuity is one of the foundational elements that should bring to something called organizational resilience. Organizational resilience, they can seem pretty abstract, and sometimes it is. It's one of those things where the risk of getting blue sky, of talking for talking is very high. And often is a result is done to cover up. But in the very basic assumption is the ability of an organization to anticipate, prepare for, and recover to incremental change and sudden disruption based on the standards. And for the British standard, it is also different level of maturity, depending on the level of implementation and the measure adopted in each organization. It is a tool or a concept that can be used to adapt to situation of growing uncertainty and interconnected society and economics. In all this, think about now, you have your sign-up. You have what my colleagues implemented in the engineering side. If we adopt a perspective of continuity management and organizational resilience, then the question changes. It's not just how the sign-up works. It becomes, what are the challenges and the operational criticalities that could limit the integration of that technical component into practices of continuity management? So like how it will influence the continuity planning, the creation of plans, procedures, and tools within an organization, or in larger terms of organizational resilience. So the flexibility of the organization itself as a whole, including both the procedure, like the function of supply chain, how you're going to shift to another supplier, or what you have to activate to stop a train that is running. Or if you are, for example, a very big industrial cluster, you have this signal. How you are going to use it to stop your most critical process, the one you cannot have disrupted for too long. How you're going to train your employees to do that? Or are you going to evacuate some employees more than others or not? So in the moment in which we think to this perspective, the signal itself changes completely natural. It becomes a tool in a wider process of knowledge of the organization and adapting the organization to sudden change. And for example, the alert itself, the time that we gain with the alert, it becomes a series of procedures we need to activate to preserve our organization and the continuity of our organization. So the question is, what do I need to do first? What do I need to do second? How this is going to be planned? And what are the implications of this planning? So do I need extra permission? Do I need a legislative framework in which to act? Am I accountable or not? So to do that, it was not easy. And the problem was that we decided to try to apply something new. And we needed methods and we needed benchmark. We decided for a case study that is Mexico City to create synergies between different projects we had and using some connection we had. So this is a very particular case because 1 million people, there are different levels of vulnerability and high exposure, as you all know. In this case, the earthquake early warning evolved a lot since the 80s with scenarios that could trigger an alarm from magnitude 5 and 6 if it is near to the epicenter. So it was well developed. The signal was there. There were 12,000 warning speakers installed just in 2015, but there were some issues that we were aware of, and the literature stated very clearly. There were, first of all, a conflict between public and private services. So the one you see there is one of the private supplier that is taken from Wired, but you can see many. So many of the signals that may give different information. There were some steps in the legislation, so critical infrastructure were required to install these devices, but there were some different gaps, confusion, and in terms of governance, and then not all the things we were clear. So there was the need for stepping beyond all this and trying to see it from an operational perspective, seeing how can we help organizations when they have an effective signal to translate it in something more useful to prepare, adapt, and recover fastly from shocks. So how can we translate that from being just a technical component into something that can help better organizations? The method we approach is we developed questionnaires, so statistics, and semi-structured interviews, so qualitative analysis for achieving in-depth knowledge. So we put together the pie chart together with the qualitative understanding of what was going on. We targeted organizational representatives in the public and the private sector and local academic experts. There was a great field work with our former alumni and student, Dr. Omar Velasquez. You can check his LinkedIn if you have time. And we developed, thanks also to Omar's field work, better connection with the RISE Mexico that supported and the data collection forwarding within their network, the questionnaires. So following to the private sector, our questions, and the Autonomous University of Mexico. So what we were trying to test, if the integration of technological component of early warnings in business continuity and organization resilience was affected by gaps such as critical information, the context of the warning message, coordination and dissemination procedure existing, for example, who have access to complex warning, including warning times, how this was relating with the organization, the implementation of business continuity plan, training and education strategies. So how these technological components were implemented into something that was procedural and practical. And then if there were gaps in the attribution of jurisdiction and holding people accountable for doing, or organization accountable for doing something or not doing it. This was challenging. The first thing we did is that how do we benchmark that? How do we measure it? So in particular for the questionnaires and the qualitative analysis, we needed a tool. Normally in social science, we use something like Likert scale when somebody asks you stupid questions and say, oh, please answer 1 to 5. That was not enough for that context, in particular for what we were wanting to achieve. So we developed a Likert scale, an adapted model, easier for stakeholders that maybe didn't have the time, maybe didn't have all the different levels of differences between things, and that was more approachable. That has been published last year. So we had a value 0 to 3 for doing the assessment. So when we were asking questions, most of the questions were benchmarked to these values, where 0 to 3, where 0 was no little, and then was arriving to most, in a also traffic-like system. So if you ask me, oh, how develop your business continuity plan, where 0, red, nothing, and 3 is a lot, I can intuitively answer. Second point, the gap. We were trying to check a gap. The equivalencies of 0, on the zeroable state, while 3, the zeroable state. Then capacity level, from non-existent to comprehensive capacity. And then resilience level that was benchmarked to the British standard 65,000 from no measure taken to full development of strategies. So we developed this small answer system to look at the questionnaire and see, is there a capacity gap, or to what extent the respondent thinks that we are achieving resilience, or the organization are achieving resilience. And this is being published on free open access. If you want to check it, you can use also for your data field surveys. The preliminary results look like that. And this is a forthcoming publication we have for disaster. We need to resubmit after revisions. But we had some very interesting outputs. I will go toward in a couple of minutes to the key findings. We had a quite big data set considering the situation, 15 semi-structured interviews, 78 valid questionnaires from Lee Civil Protection, Education Institute, and Enterprise. That for mixed method is quite a lot. And considering that ARISE network that includes private sector organizations is about 300 organizations across Mexico. There are a lot of informal reality in Mexico City and that are not very accessible. So this data set is quite solid, we would say. There provides a complementary view from different sectors. On the versus side, we have seen that the response rate was very high, in particular in education, as they were supposed to implement earthquake early warnings. And in another case, instead, they were a bit more pushing back, like, for example, transport sector. But what we have seen is that there were discrepancies. All across the data set, even doing the statistical analysis in comparison, we have seen that the technical component was there, but when we are thinking about the gaps that we can face, it's not just a matter of challenges of dissemination, how the message is going to go through, is how we integrated it in something else, how technology becomes something that can be done. So, for example, here we can see that the question if the earthquake early warnings are taking consideration how they can be integrated in organizational needs. Well, most of the answers are concentrated on the fact that the system requires updated. So it's quite mature. There have been a lot of progresses, but it's not a desirable state, right? And in particular, it tends to go overall on something that needs to be improved. And then we can see that one of the critical issues can be policies that are not updated. And it's interesting to know that in the answer, we also have seen that there was a critical failure. That was a lack of awareness about what official institution should release the warning, because half of the respondents got wrong who was supposed to lead the response. That reveals a problem between the public and the private component of the earthquake early warnings that can orient how then the organization needs to plan and prepare for. The other thing is that, are there specific plans in place, like the example I made of the train before, or stop a specific production process? Here we see a critical lack of something could be a consistent training on how to do it. How we prioritize it. There is a split. This split, we need to do further analysis on this, can orient who have to be the target of specific training. Like some organization probably do it better, some else no, but we see that this is a problem. And then another data that I find very interesting is how the organization identify critical function protected by earthquake early warning. This is one of the most critical things to do in business continuity. So know yourself, you are gonna be more flexible in the situation, right? So if you understand what are the most critical aspects of your organization, what are the most critical supply chain, the line, you then can integrate better the warning, right? We see here that there is a concentration on the inadequate side. So in terms of outcomes, in terms of suggestion we've seen, well, we need to be aware of who manages the organization, the planning assumption, and who is going to lead the signal. but also increase consistency and coherence in how the activity are prioritized and to what extent this is going to be done. And this can be done just using improved training and education, including the use of drills that our data shows that are not so efficient. So as a whole, testing the case study, we've seen that even when the system is technologically well developed, there can be still critical gaps and lack of maturity in how the signal is translated into practice, planning, and preparedness procedure. So I'm happy to take any question, and I hope that you found this interesting. I know that this is quite different from what you do normally, but this is something new that you can do when you face quantitative data or structural data, and you start to ask a question how you're going to integrate it in planning, in emergency management, not just on the technical perspective, but on how you can produce changes within organization. So I think my time is over, and I'm looking forward for your question if you have. I hope I didn't ruin your evening.
I think you most definitely did not ruin our evening. In fact, that was fascinating from both of you. If there are any questions, please go ahead and put them in the chat. In the meantime, I had a quick question for Gemma. It'll be a quick one because I think our allotted time is for 7:30 anyway. But I can't resist asking one question, and that is the idea of having an early warning system that goes beyond just the seismological metrics and looks at the risk metrics as well. Sounds incredibly useful. Is this something that's, your example was for a specific hypothetical school, right? So is this a method that you foresee being for single buildings or for populations of buildings? And especially for the latter, do you think that the exposure and the vulnerability data that would be needed to get to an accurate and meaningful estimation of loss, does that exist? Is that something that's further down the line?
Yeah, that's a really good question, Josh, because I think at the moment, I think one of the limitations of this type of method is it's kind of structure specific. Because the damage and loss metrics will be kind of structure dependent. Now what we have done is we've applied this to a port in southern Italy. So we've actually applied it to a whole system, and then kind of based on the interconnected functionality of the system, we were able to develop an optimal decision based on the incoming ground shaking, and then kind of understanding which parts of the ground shaking affect which parts of the system. So in theory, I think you could apply this to a portfolio, but it would then, the question becomes how kind of accurate is it across the portfolio? How accurate does it need to be? So that's definitely an interesting future question. But right now, it's very the ground shaking estimates are very calibrated on just one structure. Yeah.
Perfect. No, that sounds perfectly understandable. And yeah, I'd be quite interested to follow the research and see how it can be scaled up, because it's clearly highly useful in lots of contexts, both social protection and or protection of communities, but also on the commercial side as well. Insurers would love to have this kind of real-time feedback, or large value assets as well could also benefit from this a lot. So really great stuff. So thanks for that. I have more questions, but I am really conscious of time. Are there any other questions from anybody here? Otherwise, I think I'll call it to a close, and I might email you some questions, Gianluca, if that's okay.
Yeah, sure.
Okay. Well, then let me stop it there, because we were aiming for 7:30. And just to say a huge thank you to the speakers. I think it was clearly very interesting. Again, I do have more questions, but I'll keep them to myself. And I'm interested to follow your research. Also, congratulations on winning the EEFIT grant, and thank you for applying and for providing such great research out of it. And again, to those that are listening, thank you for spending your time here with us this evening. And if you are interested in finding out more about EEFIT, the research grant, or getting involved more generally, then either contact myself or just Google EEFIT. Thank you, everybody, again, and have a great evening.